And we start with Daniel De Andres, which is right there, with machine learning from the 300 simulation project, or is it the 300? Okay, so that's a typo. I thought it was a funny thing. Anyway, almost. But I want also this thing to show on the right screen, otherwise, yes, there you go. So you have slides and you will have sound.
No?
There you go.
Can you hear me? Oh, okay, nice. Okay, is this?
I'll run you 3.
Okay, is this working? Yes, yeah, it's working.
I'll run you 3 and 1. Okay?
Okay, thanks. Okay, first of all, thank you for having me here. I think this is a great opportunity for me to share my work with you. I am Daniel De Andres. I'm a second-year PhD student working in the Universidad Autónoma de Madrid, and I'm going to give a talk about machine learning within the 300 simulations. I'm working under the supervision of Gustavo Yepes, but we have a group of machine learning in our simulation project, and we have also the collaboration of a company, which is called Nova, and they're helping us develop artificial intelligence algorithms. Well, the 300 simulation is aiming at simulating galaxy clusters, which are the crossroads between cosmology and astrophysics. They are really interesting for cosmology because they are the biggest object in the universe, and you can, from their mass, you can estimate cosmological parameters using cluster counts. But they are also very interested in studying astrophysics because many astrophysical processes are involved in the intra-cluster medium, like cooling, star formation, supernova feedback, AGN feedback. So they're very interesting objects. Okay, this is the project. This is an international collaboration aiming at simulating galaxy clusters. It's called the 300 project. It is based on the zooming technique. So we zoom regions of 15 megaparsec of radius around the 324 most massive clusters of the 1 giga-parsec MultiDark Planck simulation at resolution 0. One very interesting thing is that we have, for the same objects, we have run 3 different hydrodynamical codes for the baryon physics. We have run the gadget music, the gadget X, and the gizmo Simba codes. So we can simply test different baryon physics of the same objects. We have 120 snapshots for different redshifts, and we have run the Amiga Halo Finder. We have lots of properties. We have also mock observations for these clusters, Xray, for different telescopes, SC observation, optical observation. We have also lensing weak maps observations. We also participate in providing mock observation for different telescope that made project and the NICA2 collaboration. Okay, in this talk, I would like to mention 2 projects that I've been working. One is the progression of baryon properties from dark matter Halo catalog to obtain like light cones, full sky light cones observation of Xray and SC. And also, since this talk is about imaging, I would like to talk about how to infer the masses of Planck-Compton parameter maps using deep learning. So first, I would like to mention a few things about this project. So it's based on since. So as you know, you have we have dark matter only simulation, which has a dark matter catalog, and then we can use the zooming technique to generate the 300 simulation. So we have a baryon catalog and a dark matter catalog, and then we can simply use machine learning to populate the whole MultiDark simulation with baryon properties. So this project is simple in this regard, but the only complexity is that we have, a lot of dark matter variables that not all of them are important. And I would also like to mention that, we tested different machine learning algorithms, but given the nature of our data, like the string gradient boosting is the best algorithm to solve this kind of problem. I just like you to mention that we have generated a catalog of baryon properties, so the gas fraction, star fraction, baryon fraction, and they all follow, when they are applied to the full MultiDark dark matter only simulation, they all follow the similar statistics. We don't see that the scatter is, so the scatter is not really the same, so this method can be only be useful for statistical purposes. So you have a big catalog, and you want them to have the same properties of the 300 simulation. This is a successful method to populate the whole dark matter catalog. We have also provided the integrated Compton parameter, Xray, flux emission, and the temperature of the gas. And well, this will be available for free, and maybe people can play with it. Well, another project is estimating the mass of Planck clusters using deep learning. Well, as you can know, galaxy clusters are the biggest objects in the universe, and they can be observed through the inverse Compton scattering. So this is like you have photon of the CMB, and you have electrons that are in the intracluster medium, and then you can measure this photon which is scattered from this electron of the clusters. So the Planck collaboration has created a full sky catalog of these clusters, over 1,000 clusters. So you can simply see the photons of the HC effect of the full sky using this catalog. So the problem comes when when people want to measure the mass of these clusters to do cosmology. So when they want to measure the mass of the clusters, they usually use this scaling law, which can relate the mass of the clusters with the integrating signal. So this is you integrate the signal over a certain radius, and then you obtain the mass which is inside this radius. But in order to calibrate this scaling law, you need to first measure the mass of a bunch of clusters. So, and in order to do that, they assume hydrostatic equilibrium, and they say that assuming this hypothesis, they reported a bias of 1 minus the bias is 0.8. So it's like the mass that they obtain is smaller than the expected true mass of the cluster because of this hydrostatic equilibrium. So one way to address this issue is to train a convolutional neural network on simulation, aiming at predicting the total mass of the clusters, because in this way we don't assume any a priori symmetry. What we assume is the physics of the simulation and the observational properties that these clusters might have. So we aim at computing the total mass of the clusters using a simulated data set of these Compton photons, and then we aim at predicting the real mass of the Planck catalog of clusters. So first I'm going to describe how is the data set. So the data set is based on extracting these 7,000 clusters from the 300 simulation, and we take 27 different projections of every single clusters. And well, the thing is that these clusters have to, so the 300 clusters are the blue points, and they are selected to cover in mass and redshift the Planck distribution. So at the end, you find almost full coverage of the Planck clusters, and then to improve the performance of the CNN, what we do is to train 4 different CNNs for 4 different redshift ranges, from 0 to 0.1, then 0.2, then 0.4, and 1, because of the nature of the data, and the resolution is very different from cluster at redshift 1 and at redshift 0. Okay, this is how our data look like. We can, so this is the simulated 300 Killing-Monk data, which is the signal taken from the gas distribution of the 300 simulation. What we have is simply the clean signal, which has the same angular resolution and that Planck observations. Then we introduce the power spectral, so the statistical noise of the Planck observations. So as you can see, this is the same cluster as this one, but with the Planck noise. And this is one observed Planck real clusters, which has a similar mass of the simulated clusters. So, well, this is a more massive clusters, 15. Yeah, this is more massive clusters. Another magnitude more massive, but the redshift, for instance, is smaller, so that it looks like it's a very small clusters, but still, even though with the noise levels, you can appreciate that there is an object here. Okay, I would like to mention about the CNN that we have used. We have used the VGG network, which you might well know. It is based on convolution and pooling layers for feature extraction, and then a fully connected layer for regression to obtain the total mass of the clusters. So this is a supervised learning for obtaining the total mass of the clusters. This has been applied in the literature for simulated clusters as well, but never with these noise levels and redshift ranges. Now I'm going to show you the results of this method. These are the results on the simulation. What we show here is the relative error, so the relative difference between the CNN mass and the true mass of the clusters in simulated data. And this is for clean data. This is for mock Planck data. The black line is depicting the median of the distribution, and the shaded region is the 1684 percentile. So as you can see here, the effect of adding a statistical noise to your images is simply, well, it's not affecting the prediction of the median value. What it is affecting is the scatter of the prediction, which goes from 10 to 17%. Well, but what happened when we try to predict the masses on the real observations? So now we cannot compare with the true mass of the cluster that we don't know. But we use this to compare with the mass estimated by Planck using this scaling law. So the mass that they have reported, which is supposed to be biased by a factor of 0.2. So what we found is a dependence of the bias factor as a function of the mass. In this case, the predicted mass, the CNN mass. So for low masses, we find that the Planck masses are in agreement with our prediction, and for high masses, for high massive clusters, we found a bias which is close to the reported 0.2 value. And well, we have divided the Planck data into two different data sets. One is the old Planck data, and the other one is the golden Planck data. The golden Planck data is a subset of the old Planck data, which is based on removing the contamination from astrophysical radio sources, which is reported by Planck. So they are masked. So because we think that this dependence could be explained because of that. So if we remove all the contamination, we find that the scatter is smaller, but all the predictions are compatible. So this dependence is simply explained by the parameters that Planck uses in the scaling relation, and we use the parameters that are compatible with the calibration using the 300 simulation. Indeed, you can explain this trend. So overall, these predictions are compatible with the masses estimated by Planck. So these are the conclusion. I mean, the most important conclusion is that we have tested algorithm using the other simulation, the Gizmo simulation, the Gizmo symbol simulation, and the Mushik simulation, the other part of the baryon properties of the baryon simulation. And what we found is that they are compatible with other baryon physics models. So the results are independent of the baryon physics. Thank you very much.
Thank you. So, do we have a question for Daniel from the room? While you're thinking a bit more, there are two from the Slack. So the first one is, do you know why XGB might be working better for your problems at MLP?
Sorry?
Do you know why XGB may be working better for your problem than MLP? I'll show you the question.
Yeah, I know. So
Perfect.
This is regarding to the other project. Yeah. So yeah, I know why, because so this is tabular data. So we have a catalog which are not images, and for this kind of data, a string gradient boosting usually works better than feed-forward neural network because it is not based. So there is no like a spatial correlation like images. So this is a catalog of variables. So usually this is so in the literature, this is the algorithm that usually works better for this problem.
Okay, and the second question, while Linge Lauritsen, please join the chair. Oh, you're here, very good. So the second question was from Katarina Alves. How do you choose the redshift ranges in which each CNN is trained? And related, why 4 ranges and not 5 or 3?
Well, I choose this redshift range because I tried different redshift ranges. The first thing is to train with all the data set that gave us a really poor performance. And then, well, I choose this point because if you divide our data set in these redshift ranges, you'll find that the mass distribution are kind of uniform. So it can be, so these separation in redshift ranges are good for a particular data set, given that the mass distribution are flat. But I think a similar performance might be obtained, like separating, well, in different redshift ranges. So I mean, this is arbitrary. And well, as you can see, if you see our selection of data, well, it is kind of calling to this division. But it is particular of our 300 simulation.
Okay, thank you. Thanks, Daniel, again.